We're now on the next page. We're on page 6. Okay? Now, if the charge has a negative sign, the force is simply in the opposite direction of the positive. Now, for me, the easiest thing is to remember right hand rule for positive, left hand rule for negative. Right was always considered good. I mean, it's stupid, but it's basically what people used to think, that right was good, left was bad. Right's positive, left hand rule for negative charge particles, and you'll be in good shape. Now, the next thing I want to talk to you guys about is something that's very, very common, and that's called the mass spectrometer. Now, the mass spectrometer uses an electric field. I've got two parallel plates here with a hole in the middle of one of those plates. I've got a charge here that gets accelerated through the field that's in those two parallel plates. You've got the EMF, it's going across a 200 volt potential. You've got the charge, you've got the mass. What I would like you guys to do right now is please find out what the velocity of that charge is as it enters this magnetic field. Okay, you know that your electrical potential energy is going to be equal to your kinetic energy. Anytime a particle gets accelerated across a potential, it's going to wind up being U equals K, potential equals kinetic. Your charge times the potential difference, that's your EMF there, 200 volts, equals 1/2, times the mass of the electron times the velocity squared. Plug all your values in, 8.4 times 10 to the positive 6 meters per second. Of course, as always, if you get a number bigger than the speed of light, you probably have screwed up somewhere. Most likely you didn't take the square root, so keep that in mind. Now, the next thing we want to do is take a look, and we want to determine the direction, the force the particle receives as it enters the field. So let's take a look on the top here. Here's going to be my particle. It's got a velocity in that direction as it enters the field. Now, keep that hand rule in mind. It is an electron, which means we are going to be using our left hand this time. It's negative. Fingers point into the page. Thumb is in the direction that the velocity is, and my palm actually points down towards the bottom of the page. I know it's hard to tell from the screen here, but fingers into the page, hands held flat, thumb is towards the right, and my palm is towards the bottom, which means my force, I write F sub B from force for the magnetic field, is towards the bottom of the page. That means this guy is going to start to do this. It's going to start to move down like that. If I do the same thing for that position, my velocity would be tangent to the direction of the curve there. Twist my hand a little bit, the force is going to be in this direction. So it's going to continue to turn. Force is going to be in this direction. Continue to turn. Force is in that direction. And you can see that the thing is starting to make a circle. That the force is always going to be pointing towards the center of that circle, which means your magnetic force acts centripetally, acts towards the center of the circle. Now, we've just drawn that path. The next question asks us to find out how far away that particle is going to hit, from the entrance point. In other words, what is this distance going to be? Based upon that distance, if you know what the charge is, you know the magnetic field, you can figure out what the mass was of that particle. But we're going to work it the other way around. We know the mass. We know the charge. Let's find the distance that it's going to strike this plate here. Usually it's some sort of detector. It'll glow or something so you can see where it hits. How much mass is going to be there? Well, just like usual, we're going to start out with our old friend F equals ma. And we know that it is a centripetal acceleration. It's going around in a circle. There's only one force acting on this. Force from the magnetic field is what's acting centripetally, equals mv squared over r. All right, now let's put this in here. We know what the force is going to be. Well, we know what the equation of the force is. The force on the particle is the charge of the particle times the velocity of the particle times the magnetic field strength is equal to mv squared over r. Oh, how nice. The velocities drop right out. We're trying to find r. So r, if we do a little algebra on this, is going to turn out to be mv over qb. We know the mass, 9.11 times 10 to the negative 31st kilograms. We know the velocity. We solved it up before. It's 8.4 times 10 to the 6th meters per second. We know how strong the charge is. It's got a magnitude of 1.6 times 10 to the negative 19th coulombs. It's an elementary charge. And the magnetic field strength that we're going to be going through, it's written up above, 0.5 teslas. All right. And we'll crunch that through.